Alright, I am showing you my mini project. It was pretty basic. I wanted to make a musical tuner and that would show error in pitch. And pitch is, related to frequency. Not linearly, actually, but it's easy enough to extrapolate it. So here I'll just run it. Boom. Simple as that. That was the C note. That's actually C4, centered around like 262 hertz. Not very flat or sharp because it's coming from a piano. Should be relatively in tune. And here you can see the fundamental, 261.1, which is about a hertz off. Well, actually not even. Yeah, it's very close. And we can do that for another one. This is a D, so one step above. This is a D4. Not very out of tune either. Again, a piano. But then if we change the instruments, it actually gets a little bit harder. This is me playing the saxophone. And there you go. So I actually tuned it with a tuner to be 20 cents flat. And that's what I'm seeing right here. And that's what it corresponds to hertz. And that's the percentage error. And I was playing a B flat. Concert B flat, which is my G. In any case, it's more complicated because this is full of different overtones and harmonics and inharmonics because there's a lot of constructive and destructive interference with the actual pressure waves being generated. So this and multiples of 460 create all these high frequency content, and if you just look for the highest one, obviously you see here it would be wrong. So I had to use this equation, which basically relates everything to a center, which is 440, that's A, and that will kind of give me what octave it's in, and I use that to determine the lower one to find the fundamental. And that's the tuner, but I did some chord analysis too. I wanted to do it a different way, but the way that works is this one. And here we have three notes of the C major chord. It's C, E, G, the fourth ones of those order. And it actually, I did basically the same thing. I just looked for three of these amplitudes filtering in the fast Fourier transform. Originally, I had wanted to do more complicated algorithm involving spectrographs. So as you can see, it's a little bit wrong. That's a half step too high, and that's that's 3 semitones too high. No, it's 4. In any case, and so that's what the spectrogram looks like. It's basically fast Fourier transforms over time. So each one of these is like a slice of a fast Fourier transform. And the actual algorithm I was following is right here. You get the audio, you take a spectrogram, you filter it, and then you do a chromographs, which is basically relating zones of frequencies into bins of frequencies, and then you analyze the amplitudes and you get kind of scores. Like real quick to show you, this would be kind of, each one of these is a chromograph, and you say, oh well, if this has an A, an E flat, and a D, that's this chord. But I couldn't get that to work, and I found this other method to work just fine. So I'm a little over, but there you go. That's my project.